Into excitation-contraction coupling of the skeletal muscle. So what is excitation-contraction coupling? It's how your skeletal muscle, meaning the voluntary muscles of your body, work. So if you didn't know, you have three types of muscles: skeletal muscle, cardiac muscle, and smooth muscle. And out of these three muscles, only your skeletal is voluntary. That means you can move it at will, consciously. So you should be aware that this voluntary movement which you need, like for example to pick up a pen, to walk from point A to point B, requires certain things to take place, a certain algorithm which we will go through, which allows you to cause contraction of the muscle. So let's get into the structure first of all. So here I've drawn a cross section of a muscle. So this is the muscle belly. Imagine that it's stuck to this bone, and I've just taken this muscle and I've made a transverse section of this muscle over here. Now if we look at the muscle, the outside of the muscle is covered by a connective tissue layer called epimysium, and then under that there's another layer of connective tissue called perimysium, and then you have the endomysium. This is the innermost type of connective tissue. So what happens is you actually have these muscle cells which we call myofibrils. Okay, so a muscle fiber or a myofibril is a muscle cell. So it looks quite long, and yes, they are quite long, because this one cell extends from one tendon all the way to the other tendon. One single cell, it extends all the way across the entire length of your tendon. So I'll just draw that in red for you to understand. So imagine your big muscles in the body, like the longest muscle is the sartorius muscle, or even the other long muscles are the quadratus muscles, the quadratus lumborum, and your hamstrings also. Now those are quite long, and imagine a cell that is going from all the way from one end of that muscle, from one tendon and to the other tendon. So these muscle cells are quite long, and since they are skeletal muscles, they tend to be multinucleated. So just be aware of that. It's a good histology thing. Okay, cardiac muscles are single mononucleated. Even smooth muscles are single uninucleated. But if you look at your muscle fibers, they are multinucleated. So it's because during embryogenesis, they actually start up as many different cells that join end to end, and then they fuse, and then all those nuclei come together, and you get these multinucleated cells over there. Okay, so it's a single cell because they fused during embryogenesis. Think of it that way. Now, your myofibril is a long muscle fiber, and it is covered by the endomysium. So it's covered by the endomysium. This is a layer of connective tissue that surrounds and wraps each and every single muscle fiber or muscle cell. Now these myofibrils, if you look at them, the ones that are in red in red over here are, yes, in red over here are single fibers. They get grouped together into little groups over here, and these little groups get wrapped up into perimysium, what we call perimysium. So the connective tissue, perimysium, is wrapping a bunch of these muscle fibers. This perimysium, if we look at it here, so this green color which I'm just drawing over here, this is perimysium, which is wrapping a bunch of individual muscle fibers, and they give little processes, little extensions that wrap individual muscle fibers, which become your endomysium. Okay, endomysium. So the endomysium is like an extension of a flap of the perimysium, which wraps the individual muscle fibers. And then you have these fascicles, all of these muscle groups that are wrapped in perimysium. All of them come together, and the entire muscle is wrapped in epimysium. So you have the epimysium over here. Now the epimysium wraps the entire muscle, which has got all the little fascicles of muscles which are wrapped by perimysium, and then those individual muscle fibers are wrapped by endomysium, which are all extensions from the perimysium. So the connective tissue, this is the organization, and they play a role in adding some elasticity to the muscle and helping in organizing the muscle. And that's how your muscle is organized. Now let's look at an individual muscle fibers or a muscle cell. So here we have a picture of, I've drawn this picture of a muscle cell or a muscle fiber in a skeletal muscle. And I need you to understand that this is a striated muscle. So it's striated. What does that mean? There are these, it looks like a zebra, black and white stripes over there. So you get alternating dark bands and light bands and dark bands and light bands next to each other when you look under the microscope. Think of a zebra over there. So the alternating dark and light bands are because there is a sort of level of organization of your cells that take place. And think of a crystal lattice. It has good organization. That's what makes it a crystal. And this organization allows light to pass through it in different ways. So some areas you get more light passing through, in some areas light doesn't pass through so well, based on the direction you look at the crystal also. So this is what's happening over here in your muscle fiber. You have these striations, these stripes, okay, we call them striations, because of the way that the muscle fibers proteins are all organized over here. So here we have a Z line and a Z line over here, two Z lines that I've just drawn over here, and between these two Z lines is what we call a sarcomere. Okay, so the sarcomere is the functional unit of the muscle fiber. Okay, it's the functional unit of the muscle fiber, the sarcomere, and it extends from one Z line to the next Z line over there. So you have these Z lines one after the other over here, and you have them excuse me, you have these proteins, these which are organized in a structural matrix, which constitute what we call the thick filament and the thin filament. And so you could see these zigzag lines, Z lines, which I have drawn over here. Also, we are just extending. Can you see we've just extended this image of the sarcomere, we've magnified it, and we are now looking over here. Now, between the Z lines, which constitute a sarcomere, we've got one M line over here. This M line is in the middle over here. So this M line is in the middle of the sarcomere. And from the M line, you get the thick filaments coming out over here. These are the thick filaments, which are mostly constituted by myosin. So myosin makes up the thick filament, and I want you to remember M for myosin, M for M line, so they go outwards over there, okay? And they play a role in binding to the thin filaments, which extend from the Z line. So these black lines I've drawn over here, these are your these are the thin filaments that extend from here. So you could see over here thin filament extending from Z line in both directions, so into one sarcomere and the adjacent sarcomere. So you have these thin filaments. Mostly they're made of actin, but there are a few other proteins also involved. But yeah, thin filaments, I want you to think of actin. Alright, so actin for thin filaments. There's also tropomyosin and troponin, and we'll talk about that later. So look at this, A to Z. Actin comes from the Z line. Myosin, M from the M line. Okay, that's how you remember this stuff. So what happens is the myosin is going to bind to the Z lines, the thin filaments, and pull them together and cause an approximation of the Z lines to come together. This is how you shorten the muscle. You are bringing these Z lines together because the thick filaments, the myosin from the thick filaments is binding to the actin from the thin filaments and pulling the Z lines together. They pull them together, so they just bind. They make these little cross bridges over here, what we call cross bridges and cross bridge formation. Right? And what happens is these are your thin filaments and this is your thick filament made of myosin. What happens is these filaments will slide on top of each other and move inwards. They move inside over there, okay, towards the middle. So you have these thin filaments sliding together, and this is your sliding filament theory, which is how the muscle contracts. This is what we call sliding filament theory. The average length of a sarcomere is around 2 to 2.2 micrometers. All right, so when your muscle is in the optimum resting length, or in the optimum length, optimal or optimum length, this is the best, L-A-N-G-T-H, length. This is the length of the muscle at which your sarcomeres are between 2 to 2.2 microns. And why do you need to know this? Because this is the length of a sarcomere at which you will get the maximum amount of active tension. It will generate the most force, contraction force. That's what I want you to think. So the optimal length of a muscle is where its sarcomeres are somewhere between 2 to 2.2 microns. And why is that? Because at this kind of length, your actin and myosin filaments are maximally aligned. They're aligned face to face. You're not wasting any of these cross bridges that are formed. Every myosin is paired up with an actin over there, so it will bind to something. If you overstretch a muscle, what happens is it will not all the myosins can bind to an actin. It won't be there. And same thing with shrinking the muscle. That's why they say stretch before you exercise, and this generates more strength. But you have to understand that also the stretching, it's supposed to be what we call dynamic stretching. I'm veering off topic a little bit, but I want you to understand this. It's still applicable over here, dynamic stretching. So what is dynamic stretching? Dynamic stretching is like when you're not just doing some light stretching where you're bending over and touching your feet and doing those hamstring stretches the way you think normally before sports. If you really want to make some good stretches, you should move your legs. Like you see these martial art movies with the kung fu people swinging their legs and kicking 100 times. That is dynamic stretching, where they're moving their body and causing the stretching to take place at the same time. However, if you look at static stretching, it's like it's sort of like holding a pose and trying and stretching the muscle bit by bit even more and more, and that's not the best way to actually generate force according to most sports scientists out there. So the optimal length usually corresponds with the resting length of the muscle. So this resting length of the muscle is when you assume the resting position for a joint and you relax the muscle. Usually that corresponds with the optimal length for most muscles, not all of them. And that is where your sarcomeres are at around 2 to 2.2 microns, and they generate the most amount of force for contraction. Your minimum length of a sarcomere is around 1.6 microns, and the maximum length you can stretch a muscle to is 3.6 microns, and beyond that you can actually snap the muscle, so you don't want that to happen. So now let's see this one, further organization over here. Now you could look at this sarcomere and you could see that there's the M line in the middle from which the myosins come, and the actins I've drawn in black, the thin filaments coming out over here. Now you could see there are areas where the actins and the myosins, they overlap. There's an overlap taking place. Now this part where the overlap is taking place is what we call the A band. So I'll just come back to this later. There's some more to talk about, but now look at this picture over here. Now you could see sorry about that. Yes, I think we will just use this diagram itself. Okay, let's just modify this diagram a bit and remove this from here. So now look, where there is actin, you see the green myosin and the black actins overlapping from one end to another from the M line. This part is called the A band. A band. It is also known as the dark band. So A band means dark band. Second alphabet of dark is A. Just remember that. Okay. So this is also known as the anisotropic. A is for anisotropic. Anisotropic band. Okay. And next to the A band in the sarcomere, you've got this area where there are only thin filaments, where the myosin is not reaching that deep over there. So this part next to the Z line on both sides corresponds to the I band. I band or the light band. Okay, the light band.